So today we will talk about Waring's problem. It will be an application of the sum we saw 2 classes ago, that is the exponential sum that was bounded by Weil, and which we also derived some non-explicit bounds proven by Fürstenberg in a very elegant way. But what we will use today are really the explicit bounds given by Weil. So what is Waring's problem? It comes from, of course, Mr. Waring, who at the end of the 18th century had a little book where he stated several conjectures. It's called the Latin title translates as Algebraic Meditations. And so he more or less conjectured what is now known as Waring's problem, or Waring's conjecture, I suppose, though the conjecture, qualitatively speaking, was already proven 100 years ago. So Waring stated that, well, I don't remember whether it was after or before him that it was proven that every integer can be written as a sum of 4 squares. I think it was already known, but he conjectured that you can also write every integer as a sum of 9 cubes, say. His value was actually not optimal, and say 17 fourth powers, he conjectured, though again 17, I'm not sure 17 is best, I think it is already known not to be, and so on. So the question is then, is it true that for every k there is an n such that every large enough integer at least can be written as a sum of kth powers? Well, if every large enough integer can be written in that way for some n, the statement follows for all integers. You just choose, if needed, a bigger n. But
so sum of non-negative.
Non-negative. Yes. Let me state it. So, for us, it will be a good excuse to use the results from 2 classes ago, and also to see in action what is known as a circle method. So, what is Waring's problem? Show that for every n there exists a k0 such that for all k bigger than k0, no, it's the other way around. So show that for every k there exists an n such that this equation has a solution in non-negative integers for n large enough, meaning larger than a constant. So as I was saying, if you prove this for n large enough, then you have proven it for all n. You just pick a little n as big as big N, or as big as your little n was, whichever is larger. So in this qualitative form, this was proven by Hilbert. So the second proof, which is what really we will be talking about now, the second proof of descendants, comes from Harald and Littlewood, and that was very important because it was their second application of their circle method, and of course a method becomes a method only the second time you apply it. Before it's just a solution. And also they managed to give asymptotics. So as n increases, they give asymptotics for the number of solutions. this is really important, the circle method. So as I said, it was the second appearance, and then they had a series of papers where they applied it to many problems, including, for example, ternary Goldbach, as you know from my talk, if you came from my talk some time ago. The first appearance was actually in a paper by Harding Ramanujan. No, but that's a very special case on the partition function. Now they had n greater than k times 2 to the k. Well, they managed to do a bit better, more like k minus 2 times 2 to the k. But this is pretty large, right? So the bigger, if you want to make the result stronger, you want to show that it holds for smaller n as well. So this has been improved many times. So notably, well, the biggest improvement or series of improvements was due to Vinogradov. There's also Hua, quite important. And then the most recent, so there were several other people involved. So Vaughan, and there has been the best result, depending on what you mean, whether existence or asymptotics, at any rate, the best results right now are those due to Woolley. So right now we are at, well, essentially nk squared for asymptotics. It's a constant. And k log k for existence. In the case of existence, we actually know much more than, we know less than asymptotic, but we know more than what's known in Hilbert's day, in the sense that we do get asymptotics, just not for the unweighted number of solutions. People use some weights that make life easier, but also mean that you're counting something else. Very well. So what is the circle method? So the circle method, just two things. So it gives asymptotics, and methods that give asymptotics generally work only when there are many solutions. Very well. It's a bit cold. May I close the window?
Yes.
So, for example, if you wanted to it's very difficult to apply to problems such as sums of very few cubes because there are few solutions. So in fact there are some open problems for low powers and the sum of very few powers, say the sum of 4 cubes. And it's very difficult to tackle that with circle method because there are not enough solutions. And you certainly cannot tackle, say, sums of 4, well, say sum of 4 squares is already a mess, and you could not get something like even Fermat's characterization of the numbers that can be expressed as sum of 2 squares. That's algebraic. This is analytic. It works wonderfully, but generally when there's something that is large and a large number of solutions, it can be estimated. It's very hard to estimate something small or something rare. So it counts the number of solutions. To an equation in a box, say 0, m to the n. How? Well, it's just by means of an integral. The number of solutions is equal to the integral Yes, why is this? It's because you're going to have that inside here, you're going to have an expression of the form E alpha n, where n is just the sum of f of x and big N. But this integral here is 0 unless n is 0. So it's 1 if n equals 0, 0 otherwise. Very well. Yes?
How k is involved in this formula with numbers?
It isn't yet. It's not involved yet. I'm stating the circle method in full generality. So you're counting, in this case it would be, it's just some sort of polynomial, say. It can be polynomial, it generally is. So here the polynomial would be the sum of the case powers of x1 up to xn. That's what would it be, what it would be. But in general, we can do this for a function f. And this is how case powers are involved. That's the definition of f. That's all. Yes. So of course you can also say this in the terms that I explained in my lecture on 3 primes. You can see it as, well, you have a triple convolution, or a case, in the case of 3 primes, here it is a convolution of n functions, and its transform is the product of the convolutions. This is what we're going to have. You see, you have an nth power here. That's a wonder of a Fourier transform. It's hidden here, the idea, but it's very simple. It's just that you realize what's going on here. You realize what I have done here. I'm just using the fact that yeah, so E alpha, so I'm doing a sum over all vectors m, and here I have the function, but this is just a cube, oh, not a cube, but an nth power. Right? So this is a nice thing about a sum. There are also uses of the circle method for general f. F doesn't have to be quote-unquote diagonal. It doesn't have to be the sum of n identical terms. But it is the sum of n identical terms, and your life is particularly simple. Because it's just an integral of a power, basically, times a phase. Is everybody happy so far? All right. So we must study. We already studied this when we were doing, remember the lecture in which we gave an ergodic proof, and before we had given actually a more explicit analytic proof. I will remind you of what we proved. So this is Weil, not Weil, but Weil, very different. Have that S alpha is going to be at most a constant times m to the 1 plus epsilon. Oh, we can do it from 0 up to m if you prefer. Here you're going to have n to the, what is big K? Big K is 2 to the k minus 1. So Vinogradov here had a better result, but this is the result that we proved. So of course this looks slightly complicated. So let me simplify. So 1 m to the 1 would be a trivial bound, so it's m to the 1 plus epsilon minus delta over big K. So delta will be a bigger number. All right, so you get a gain, a power gain, not a huge power, but still a power gain. Since you have a delta over k that you're saving in the exponent. Very well. So we have a good bound of S alpha when alpha is close to a rational whose denominator is not very small. Now, by Dirichlet, any alpha is close to some rational, very close. In fact, so if its denominator is not very small, we use this. If its denominator is very small, we call that the major arc, so we use other techniques. So let me be formal about it. So big M for major. So the major arcs, they are when we take the circle and we take some arc around 0, a somewhat smaller arc around 1/2, another around 1/3, and so on. I haven't written. Yes?
Dirichlet theorem said that we have infinity many such Q, no?
Sure, but it yes. It depends on the exact statement, but yes, of course, it does unless you are a rational. If you're a rational, you have only one good rational approximation yourself. Yes, but this is yes, that's fine. I'm just saying that if I define things, and let me just state that if I define things this way, for Q0 considerably smaller than big Q, say Q0 smaller than big Q over 2 already, then you are going. The arcs are not going to overlap. It's all that we care about. So, exercise, arcs do not overlap for Q0. So, yes, this is important. You have some sort of set big Q, so every alpha will be approximable by some, will be at this sort of distance for some little q up to big Q. But if little q is smaller than big Q0, which is a smaller number, then we call that a major arc. And everything else will be, so everything else so by Dirichlet, for every alpha in the minor arcs, there exists an A over Q, Q bigger than Q0, such that, well, it's between big Q0, such that alpha minus A over Q right. Very well, so we will choose big Q, M, K, minus a delta minus eta. Delta and eta again will be small, but especially delta will not be too small. And q0 is m to the delta. No, simply so that they correspond roughly to that inequality over there. Very well. So because every alpha in the minor arcs is close to a rational whose denominator is not too small, it's bigger than q0, you're going to have a good bound coming from Weil. You see? So we will not have to need to worry so much about the minor arcs. We will compute their total contribution at the end. But it will not be so large, simply because it is a bit smaller than the trivial bound, and if you raise it to a k power, to an nth, a kth power, yes. You raise it to an nth, or to an nth power, excuse me. Once you raise this to an nth power, this gain gets, of course, amplified. We will be worrying today mostly about the major arcs. I will compute the minor arcs at the end. Actually, of course, what we care about is an integral of a power of this over the minor arcs. So as you might expect, just using a maximum bound like this one is not the most efficient way to go about it. And there have been many improvements which focus in part on that. But we will not actually be doing, as usual, I will try to give you a complete proof, giving you the main ideas, and I will tell you at the end of some of the later history and of how things were improved. So what about the major arcs? So we have, of course, alpha is equal to a over q plus theta yes. Now an S of alpha, well, we can write it, we can split by congruence classes. This is a little crude, but it's harmless. B mod q, E or A over q, bk. So what have I done here? I have done two things. So first of all, I have separated A over q from, I have separated A over q m to the k from theta m to the k. But E A over q times m to the E A over q times m to the k depends only on the congruence class of m modulo q. So I can write E A over q b to the k. What should I write here? All right. What am I doing here? What did I just say?
So why q divided m? The first question.
Who says that q divides m?
Okay.
Let me write it slowly. So this is just agreed, just by definition, where I have S alpha over there. Yes? Now, do you agree that the value of this depends only on the congruence class of m modulo q?
Mm-hmm.
So I can write outside b mod q E a q b to the k, right?
Okay.
Everybody happy now? You know, please interrupt me, because if one of you is not following, probably other people are not following either. Now what do I want to do? I just want to approximate this. I want to do something very prosaic that we do every day. I want to approximate a sum by an integral. No. So let me use a pretty brutal method. So if I approximate a sum by an integral, in fact, what I'm going to have is what? I can simply say, well, this my favorite way to go about it would be as follows. I say that f of n is roughly the integral of f of t from n minus 1/2 to n plus 1/2. Roughly. Of course, there's going to be an error term in terms of the derivative of f. So what I can say, yes, even that I am being a bit brutal, I can just say is that. So of course these two things are one and the same thing. So this is 0, and now I'm going to have the error term corresponding to 0m f of t minus. So the meaning of this sign is clear, right? Just means the smallest integer larger than t, or no smaller than t. Plus, of course, f0. Now, who can tell me what the next step will be? So how do you estimate the difference between f of t and f of ceiling of t? Yes, you can estimate it, or even more primitive. Yes, the first step would be you estimate it is the integral of the derivative over on the interval t comma ceiling of t, and that is bounded by the length of that interval times the derivative. But in fact, we don't need to take the maximum of the derivative right away. I can just write oppa so let me be just a tiny bit more clever. I will actually, I write this integral down, and now I'm going to change the order of things. Yep. Yep. So we tell ourselves, well, how often can the term f, a term for a given u appear? Well, the answer is not that often. So this would be from 0 to, I suppose, m, and here we still have the term f0. From 0 up to m, a term f prime of u can appear for only an interval of length 1. it can appear only for the t such that u is between t and integral part of n. So here you have some most fu f prime t dt, I can use a different variable, b, plus f0. And so this is, well, la 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 la. So this is just m times the max f prime u, yeah, which is what we wanted. So this is actually more, if you apply the max right away, you run into trouble. It's better to apply the max only here. Plus O of f infinity. Though this f infinity is sort of fake. It's just f of 0 plus f of about m. All right. If you wish, if we have a term like this, we call it edge effects. It's simply, the funny things that happen in the borders. In fact, I have just re-derived for you a slightly worse version of the first case of something that you probably have seen at least once in your lives. But let me give you a clue. It's a piece of mathematics that actually engineers know better than mathematicians. It is very important. It is a basic formula. So it's basically case k equals 1 of Euler-Maclaurin. Though in Euler-Maclaurin, case why I say basically, because here you do something better by a factor of 2. In fact, I can leave this as an exercise to get a factor of to improve this by a factor of 2. It's quite easy. Here we were approximating t by the integer just above it, whereas we should have approximated it by we should have rounded rather than take ceilings. And if you are within distance at most 1/2 of the integer you're rounded to. Once somebody in a bar started talking to me, and it turned out to be an old person who had studied engineering, and he started telling me of the elementary things he had done, but of course one of them was Euler-Maclaurin. And if he had put me on the spot and made me give the fully general version, I would have been embarrassed. And it's also very important because there's a story about, I think it was Vesikovich, or somebody who was at some point during the Civil War stranded in a strange place somewhere in the south, maybe in the Ukraine, and he went to the countryside to trade forks for food. He was caught by some sort of ataman who told him that he was there as an agitator and should be shot. And then he said, "No, I'm a mathematician and I was trading forks for food." And so the ataman said, prove that you're a mathematician. I don't believe that you're a mathematician. Please do the Euler-Maclaurin development of this function. And he managed, but many of us would not be able to. So it shows that you should know this. Do you know it?
Yes, of course.
Because you have had to trade forks for food. All right, so everybody knew it actually, and I was just wasting board, or not? Yes? No? You can tell me when I'm doing that all of you already know. Well, let us hurry, but please please tell me when you don't follow something and when you already know something. All right? Pact? So now I will tell you something that not all of you know. It's that you can actually do much better than this in circumstances that often arise in number theory. So this will be enough for our purposes. So if you have a function that is increasing but not too rapidly, I mean, generally things are normalized, so this is the case, and it's also convex for x in an interval, then the sum. Yes, so we will actually not use this, but you can write it out and realize that precisely under the conditions that we are in, with some normalization, you do have this, because we're working with a special case where f is of a certain special form. F is e of a function. And in this case, e of g of n, you do have that is approximated by an integral with an excellent error term. So if we did this, we could just take big Q equal to mk minus 1. You would not have to worry about the delta. I don't think whoever it was asked this when he could not have, because this came after the Civil War. So, but it's still important. You could be asked this now. All right, we will actually proceed with things that were already known. So for us, and so f prime of s is equal to, well, you know, blah blah blah. Of course, an exponential is of size 1. So this is in fact O of theta q mk minus 1 O of mk minus 1 over q, which is O of eta plus delta minus 1. Here we're just using the fact that this is less in absolute value than big Q, small q. Right, I'm just checking the derivative so that I can apply this and get something. So if I take the sum, I get, so there's a sum, I'm just rephrasing this. So this will be an integral the f infinity will just be 1 plus O of m minus b over q of eta plus delta minus 1 plus O of 1 and here what do we have? Remember that little q is at most m to the delta, so not unexpectedly this little term will disappear. It will just be eaten by the bigger term over there. All of these O's are sort of not so important. So we have here we are just going to change integrals, change variables again. We have a little term, error term that is of size 1, so I can just do it from 0 to m. E theta tk dt plus O of m eta plus delta over q. Very well. Little q, remember, is 0 m delta. All right, so we have this, which is what we wanted. So we have approximated our sum by the integral divided by q, because we're just taking the integers congruent to something modulo q, plus an error term. So we can now approximate as eta so S of alpha right, so I of theta is just what I defined over there. It's a funny integral. It's not so funny, it's the integral you expect. So if you want to be really sophisticated about this, you could say that these are the contributions of the finite places, whereas this is the contribution of the infinite place. It's very important to try to be sophisticated, right? Everybody with me? All right. And so this is, I'm just going to bound this here using the brutal bound for, it raises to the nth power, and whenever there's an error term here, I can just use the brutal bound for this. So that would be m to the, that would just be m. So here I have n minus 1 plus eta plus delta. All right. So if I take this, if I take this integral over the major arcs, I get I'm just taking the integral, so of course this m is a bunch of arcs, so I have just a sum over all arcs. The arcs are the arcs around q up to q0, and Algorithms class is A. And here I have just put, so what is C of q? C of q, this is C of q. You should have asked me, what is C of q? This is C of q to the n, e to the minus a over q n. It's simply because I have that factor, eta minus n alpha. And it splits into a over q and theta. And here I have the contribution of the I of theta. Theta varies, this is the arc. No, the arc, remember, it's centered around a over q, and it has a certain width. It goes from a over q minus 1 over small q big Q up to 1 over small q big Q. So everything is very simple. Plus, of course, an error term. But the error term is not a big deal. The error term is, what was the error term? Excuse me. What was the error term? Here I have a mod q. By the way, everybody likes the parentheses to say to mean greater common divisor, right? Okay, you don't have some funny initials in Russian. People in France always just write this. People in English generally write GCD. N-O-D. But it's fine if I just write the parentheses. All right, very well. But in fact, we can just bound this brutally and forget about the condition. I have even, let me see, did I been too optimistic here? No, here. I should not have a little q here because you see I summed it over. Yep. No, this is so sorry. This is fine, but then when I sum this, yes, when I no, this is fine. This is fine. This is completely fine. So I don't have a little q here, but here I do have a little q because it's just the width of the arc. 2, but it is, you know, off. This is the width of the arc, and I'm going to be summing, and so this gives me what? This just gives me, well, you know, because compute it all. But in the end, I get m n minus k minus 1 plus 3 delta plus 2, 8. Just substituting the actual values of q and q0 here. Very well. So this already tells you that for our purposes, delta will not be too small. Delta will be about 1/4, say, because we need this to be smaller than 1. I'm just saying that van der Korput would allow us to take delta equals 1. At any rate, this will be small. This will be nothing to worry about. Now, what can we do here? So we already have more or less what we wanted, right? But we want a simpler expression than this. So in fact, we make our life harder. No, we make our life easier, but by making our sum longer. In fact, we're going to make our sum and our integral infinite. We're going to complete them. In general, completing your sums and your integrals often makes them simpler in the end. So first of all, I of theta. What is I of theta? So I want to get some sort of approximation for I of theta. So of course the trivial bound is going to be m, but I also have a different bound. So of course you get the trivial bound from here, but we can also just, we do a substitution of variables. And we get e of u 1 minus 1 over k du. And this is going to be bounded exercise. It's just by partial summation. So this is O of little k, 1 of theta 1 over little k. Very well. This I can leave as an exercise. Very boring calculus problem, but also a very easy one. That's for n bigger than little k. we have that. We want to compute how much it would cost us to complete this integral, that is to add the tails. How much of an error are we putting in if we just gift ourselves some tails over here? So we have so this is how much it costs to have tails. So let us see if we can afford them. So we have our integral and we want to complete it. We have the integral from minus infinity to infinity, I of theta and e minus theta n d theta plus of n over q So I have that this is at most big Q0, Q, and this is just, well, it's the reason why I had a little eta to begin with, because it's going to be m to the k minus eta. So this as a whole is going to be m to the n minus k minus eta n over k minus 1. So this is good, because what we're trying to defeat, the main term will be of size big M to the n over little k. So it's good that we have something smaller than that. So we are going to be able to afford to complete the tails. And we are going to be able to work with this integral instead. No? Yes?
On this list, you prove that I of theta is less than 1.
It's less than m, and here it's also less than d. Remember, yes, but theta will generally be a small number. So if theta is 0, this is a really bad bound. Of course, fortunately, theta is not 0, but theta is pretty small. 1 over little q, big Q is pretty bad, but not that bad. We're still able to get a good result.
This inequality and is the first term constant?
No, the first term is not a constant. I'm not sure what you mean. You see, theta, in practice, theta will be really small. So this bound is not supernatural. It's not of 1.
Okay. Not, but it's a constant of m.
The constant of
m.
It depends only on m. You mean, or not? No, it does. Yeah, it's. Oh, here, yes, you do have a constant bound. That's a trivial bound, simply because you have an integral of something bounded by 1. Yes. I don't quite get it. Yeah.
And is the first term
yes.
bigger than the O? Yes or no?
It should be. Well, it's. When theta is very close to 0, yes. When theta is very close to 0, then I of theta is about m. You have no cancellation. And so you have that, yes. In fact, it's a lot bigger than this. This is going to be eta plus delta eta plus delta is going to be something like 1/4. So for theta really tiny, this is going to be much smaller than that.
Okay.
Very well. So this shows us that we can replace our bounded our finite integral by an infinite integral. And now we're going to do exactly the same for the sum. Right, why not? We also like infinite sums. Now, why do we like infinity so much? In part because infinity is elegant, but also because infinite sums can actually, and infinite integrals can often be simplified So we're going to be tricky, and we're going to use while to prove something that really is easier. C of q, so we're going to use it to bound C of q. So it's going to be less than a constant is q epsilon q minus 1 over big K q over the same big K, because you see, what is C of q? It's just 1 over q times an exponential sum. Just b goes over the integers, if you wish, from 1 up to little q. That's all. And the fraction is exactly a over q. Legitimate. Of course, usually one can give better bounds for complete sums, but we don't particularly care. Here we just want something that is good enough. Very well, so this will be enough for us to be able to complete the sum. Because then we have and this is so, well, here I'm just computing the error that's going to accumulate because of C of k. I mean, this error coming from the integral. But now I'm going to tell you really the cost of the terms that we will add to the sum to make it infinity. So, what do they add up to? So this is a sum over all q, which is 0, little q, 1 minus n big K plus epsilon n. I'm just putting in the bound from here, that's all. Am I?
Sorry, go ahead.
Yes.
And why the error is big O of L to the power K minus...
Excuse me?
Why this error?
Yes. mk mk minus eta.
It should be in the power n.
Yes. So here you're telling me, no, this is fine.
Why?
Where?
K minus minus eta.
Where do?
On the left-hand side.
Here.
Yes.
Oh, here I'm just computing the error coming from here.
But there is another power.
No, that's all. And this in
Should be on.
oh, sure. All right. Yes, but it's, sorry, you're completely correct. It's a different power, but it's still going to be about the same thing. Well, if you wish, I can just say, well, I'm just going to compute this. It's going to be simple. Are you happy? After all, it doesn't depend on anything, so you can just multiply it like that at the end. Very well, but where are we here? So here I have just taken this bound, I have raised it to the nth power, and I have multiplied it by the number of a's, which is at most q. So I have this, but this is going to converge, because if big N is big enough, because this is going to be more than q0 minus n over k plus 2 plus eta n, if, of course, if n is bigger than 2k. Pretty big constraint, but we will actually need this at the end anyhow. All right, so this is the cost of completing the sum, and this multiplied by the power of m over there is the cost of completing the integral. But in both cases it's acceptable. Well, we sum and we get I don't know whether this is a sigma or an attempt at a fracture S. Let us say it's something somewhere in between. And here we're going to have 1 plus q0 minus n over bk plus 2 plus epsilon n. That's the error term from here. Plus the sum of the error terms that we had before. So m to the, here we do have n minus k minus eta n over k minus 1, right, multiplied by 1 from over there, plus m n minus k minus 1 plus 3 delta plus 2 eta, and I think I also have an eta floating in from somewhere, right? Is it there? No, it comes in here. So I can just say delta equals to 1 for eta equals 1 over 10. Say, doesn't much matter. All right, so this term will then be smaller than, so this is m to the n minus k minus some little delta. This depends only on n k. So, and this is valid for n bigger than 2k, that is 2 to the k. So we obtain that the integral of the major arcs is equal to, well, there's an error term, and here there's another error term. In fact, this will also go in there. And what are sigma n and v? They are the so-called singular series and singular integral. Very well, we're not done yet. We still have to simplify this. In particular, we have to show that it is of the correct order of magnitude, namely a constant times big M to the n minus k. The error terms will be smaller than big M to the n minus k, minus 1, in fact. But we want to show that it is of the order of big M to the n minus k minus 1. Well, at any rate, we will get the right answer, so we shouldn't worry. So we have to show what the order of magnitude is, and in fact we will be able to get some very nice expressions. But it's already nicer than what we had before, at least the sums are infinite. So here the main reference would be Sanders. I think it's structure of set addition revisited. Maybe I'm getting a word in the title wrong, but it's mostly that. And then there is some notes by Green, which have a very similar title. So for lecture 5, this is there are two things that I'm giving references because some of you were asking me. Did anybody come into the room and wondered what I was doing? All right. So in lecture 5, I was using two things. It was section 3 from so-called additive Davenport. So Davenport analytic method for the finite equations. So this is generally called additive Davenport. That's a colloquial name for it. And I was also using Einsiedler and Ward. I forget the chapter, but there's a chapter devoted to what I did in lecture 5. In lecture 6, well, lecture 6 was pretty much my own, as in just from my ideas on how to present things. You can find some material in Iwaniec-Kowalski, but then you can find everything in Iwaniec-Kowalski, and also in Friedlander-Iwaniec. So these are two big fat books. It should be easy to find there. There's sections on the large C. And as for today, I would say the main two sources are additive Davenport, but also chapter 20, section 2 in Iwaniec-Kowalski.
What is this book, the last name?
Kowalski? Emanuel Kowalski. And that's not in Cyrillic. All right, where were we? So we want to simplify the singular integral and the singular series. So for the singular series, what do we have? So we have since. First of all, this kind of sum is a sum of a very well-known type, and it's an exercise, really. It's called Ramanujan sum. So here, when R is coprime to Q, in fact, this has size 1. This is just a Möbius function. In general, it's a slightly more complicated sum. It's still easier than the... So it's a sum over all divisors of the greatest common denominator of Q and R. So, since that is the case, we have well, this is what we had in the inner sum of the singular series, so we better do this. So here we're going to have, we put, see, inside here, I'm just reminding you of the definition of C of Q. This is going to be, by this equality, 1 over Q of n Very well. So clearly what? Well, first of all, does everybody agree? So, all right, up to here we are I'm just applying the equality above, and here what do? Well, we are here. You notice I'm really when I ask, does d divide b1 to the k plus bn to the k minus n? I'm really asking whether this is a solution, b1 up to bn, whether they are a solution to the equation modulo d. No? So this is what I'm counting. Now, what happens is that so this is clear. We agree? Now, if we consider solutions modulo d, each of them appears several times. Each of them appears q over d to the n times. Simply when we have a tuple of elements modulo d, which is all that matters here, there are q over d to the n tuples congruent to it when you consider tuples modulo q. Right? So this is the reason for the fact that q to the n gets replaced by d to the n. There's a factor of q to the, you see, there's a factor of q to the n over d to the n coming in here, because we're summing over all things modulo q. So if we sum things modulo d, the factor of d over q to the n becomes d over d to the n, or what is the same 1 over d to the n minus 1. That's it. There's nothing mysterious here. All right. So what can we say now? Well, this is nice. Why is rho n of d? What can you say about the function rho n of d as a function of d? So it counts the number of solutions to an equation modulo d. What can you say about it as a function of d? It is multiplicative, for one thing. I don't mean completely multiplicative, I mean just multiplicative. So, do we have the same vocabulary? So, a function is multiplicative if rho of a times b is rho of a times rho of b when a and b are co-prime. Yes. So, so we have that a, the function we had at the beginning, c of q to the n, e of minus a n over q, we have this. I'm just expressing this. La 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 la. Why do I say this? Why do I say this? Why do I have the minus here? Can anybody explain this great mystery to me? Why do I have a minus here? It's slightly funny. Ah, yes, it's simply because of the Möbius.
Yes, okay, so why it's not depend on K?
On K? Yes, it depends on, let me see, what did I do here? No, it depends on Q. It does depend on K. It's just hidden definition of rho n of d.
Ah, oh, yes, okay.
Very well. All right. What are these numbers? So here, I mean, to make sure that everything converges, we just need some crude bounds. So in fact, to make sure that everything converges, this is a finite product, but later we'll need to check for other things for convergence. We can just do it the other way around, right? We can write A over Z mod PZ C P alpha M E minus A and Q, and here I can write just by the vowel bounds P minus N over K plus blah blah blah, and this is less than P alpha minus 1 minus N minus K over K plus blah blah blah. So this will be fine. This is just to check for convergence later. All I'm doing is using this equation backwards with views to the future, because very soon we will have an infinite sum over things of that form, and I want to make sure that these terms are small. And so what I'm doing is I'm applying this equality backwards for the special case of Q equals to P to the alpha to get that sum back, and then I use the vowel bounds. Exactly. So that's all I'm doing. But in fact, so this gives you the decay. In fact, something simpler is true, something very neat. So rho of n P alpha minus, and this is 0 for alpha large enough. How do you call this fact? Does this ring a bell? What does this mean? This actually means, or this is true because once you reach a certain alpha, after that, you will not get any new solutions. Every solution will be continued to every solution over Z mod P alpha will be continued to a solution in Z modulo P alpha plus 1 in a unique way. How do you call that lemma? Hensel, let's call him Gensel. He will not be very happy, but he died a long time ago. So yes, Hensel.
Hence, lemma stated about the polynomial of one variable.
If you have more variables, we're happier.
Why?
Yes, set the other, hold all variables fixed except for one of them.
Yes.
Well, but the same proof works for one thing. And if all you care about is existence, you can hold things fixed and blah blah blah. Oh yeah, it will not be in a unique way anymore, but you know, you fix. No, but the scaling will be fine. Yes, it will be. Yeah, or rather, n minus 1 variables arbitrary and the last one unique.
Yes, of course.
All right, it's just me. Good point. Thank you. So just to give you something explicit, we can call this easy Hensel. I'm not sure that this is actually that maybe this is already true for alpha. Well, so maybe non-committal. This is non-decreasing. Maybe it's already constant for alpha bpn plus 2 or alpha. I think it should really depend on k as well.
Yes, of course.
Yeah, but it's actually non-decreasing for at least. Already in this range it's non-decreasing. Not that it matters. In reality, for it to be really constant, that should depend on k. But at least you could get some new solutions for k very hairy, but at least it's going to be non-decreasing. At any rate, these are just quick notes. So this means that what? Hence, what do we really care about? So the curl is sigma is a sum for k going from 1 to infinity of c, q, n. Sorry. N, e minus a n q. This is going to be the product 1 plus, and this is fine. So what follows from this is that this is a convergent product, so by this fact. So this is, well, in fact, for p bigger than a constant c, this is going to be between, say, 1/2, well, it's going to be bigger than epsilon, but say 1/2, and it's also going to be bounded by a constant, say 2. So it's not a product that, but when I say, I just need to explain what I mean by convergent product. By convergent product, I mean that it does not go up to infinity, but I also mean that it does not tend to 0. No, it's not always apparent because a sum that converges to 0 is a convergent sum. Yeah, I'm just saying that this is why I was proving this sum. All right, and this by this statement. So this is just the limit. In fact, it becomes constant after a while. Rho n p eta. Very well. So which is just rho n p to the alpha, excuse me, for alpha large enough. It's unstable. In fact, there's one step that I will skip here. So I will just say, not hard to show that in order to show this is positive, we will still have to show that there isn't a single term that is equal to 0. Because if there's a term that is 0, we still say that the product is convergent. But for all p, provided that, so here I will just give you the reference. So it is lemma 5.5 in Davenport. k even, k odd. And so, what is the conclusion? Well, our sigma n is this beautiful product here. In particular, this beautiful product will be positive. It's good to know. We want our main term not to be 0. And this depends only on n, notice. In a rather soft way. Very well. So now we have to approximate the singular integral. So what is our singular integral? So t is going to infinity minus t, big T, I of theta n, e minus theta n, d theta. So what is this? Slim t infinity 0 m 0 m. I'm just changing the order. Remember the definition of I of theta. So here we have I of theta was the integral of e of theta x to the k.
Can we stop and
Yes.
discuss about the variable statement?
Yes.
About the limit.
How the limit is non-zero?
Non-zero.
No. Oh.
Okay.
Sorry.
Okay.
My apologies. Yes. All right. Now it makes a lot more sense, doesn't it? Very well. Thank you for that. And here we have all right, but what is this thing in the inner integral? That inner integral is basically a delta function. Of course, we're mathematicians, for us the delta function does not exist, but there are approximations to the delta function. Well, it exists as a distribution, but there are approximations to the delta function, and this is one. Now you have that. So what is so e theta, and here you have r, say. It's a delta function. In what sense? So this is something. So this is something that tends to 0. If r is non-zero. So it's some series of functions like this, and becomes pointer and pointer. And it's also important that the integral, and it's actually quite easy to check, the integral is 1. So if you have a family of functions that gets pointer and pointer at a single point and whose integral stays 1, that behaves like the delta function. So there are different ways to formalize this. Let me be a bit informal about it. So first of all, what is this? This is still not mess with the limits yet. From 0 up to km to the n, simply because it's the largest value that the thing inside can possibly take. Blah, 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 blah. So here you have the volume in the sense of n minus 1 dimensional volume, more like surface area really, of, here you would have x1 up to xn up to m, such that this equals some s So here I'm just changing, I'm just replacing some variables. Yes? But as I said, this is basically a delta function. And, well, so that means that, and if you want to be really formal, you could say, oh, we use a Fourier integral theorem, we check some conditions, but technical, and it's almost nothing. This is going to be equal to what? So you have a function, which actually you can prove is nice and continuous. It's the number of solutions to this in real numbers. No? Oh, not the number of solutions, but you know, you have a nice surface and you compute its n-1 dimensional volume, meaning its surface area. Everybody agrees with this step from here to here? Yes, so I'm just replacing all of these mega integrals from 0 to m by one single integral, and in which is the value of x1 to the k plus xn to the k. And by how much do I weigh it? By this. Everybody with me there? And now I'm asking for the last step, and this is actually, this volume thing, it's basically a constant that gets scaled, or it's bounded by that. So it's a very nice function. So, and if I, as I said, if I just take the integral of a function times another function, this one, that tends to the delta function in this sense, what do you get? You get the, yes, the value of the, you know, if you take a function and you multiply it by the delta function, quote unquote, and you take the integral, you get the value of the function at the point. So you have that's it. In fact, I could even give you the explicit value here. So it's clear at least that this is a constant times this is a constant times m to the n minus 1. Yes. But I can say, so for m, say m will actually be n to the 1 over k, we get, in fact, that v this is really also an exercise. It just comes from one of the definitions. So basically you just have to look up one of the definitions of the gamma function. So we conclude. For m equal to n over, this is not hard, it's just the computation of a surface integral. So for m equals n to the 1 over k, the integral of the major arcs, so, and this will be the main term, that's why the major arcs are called major. They are really tiny, but they give the major contribution. Plus O of n to the n over k minus 1 minus delta prime. Well, delta prime will be, well, you know, something. So for our choices, I think it's 1 over k and the min of 1 over 20, 1 over 10, but it doesn't much matter really. I'm just assuring you that it's positive. And epsilon can be taken quite small. Where the curl, so a singular series is a product and the V is the volume, as I said, which is equal to 1 plus A. Now, of course, we worked hard to get this, but this result is exactly what we should have expected from the beginning. So, first of all, so there's a right scaling, big N to the. So if you assume that if the case powers were just random numbers with logarithmic density 1 over k, then what you would get would be a constant times big N to little n over little k minus 1. Why? So the number of, now that we have got here, and we worked quite hard to get there, let me explain to you why this is what we should have expected. So the number of variables is little n. Each variable has range big N to the 1 over little k. So the number of possibilities is big N to the little n over little k. Now, why do we have that minus 1? It's because there's the equation that we want to solve. X1 to the k plus to xn to the k equals big N. Only about 1 over big N values of the variables in the range will satisfy that. So we have to divide by n, and we get big N to the little n k minus 1. Now, why do we have exactly this and exactly that? So with the gamma function, we just got lucky that there's a closed expression. What really matters here is the volume and the product. Well, this is exactly what we should expect. It's a contribution from the finite places. A finite place means a prime, and the infinite place, meaning in this case the reals, the completion of the rationals. So this is precisely what philosophy would have given us, because the volume is the quote-unquote number of solutions over the reals. And for P, rho of P alpha is the density of solutions on the p-adics. Exactly. So it's the product of the densities for the p-adics times the density or number, quote-unquote, of solutions over the reals. Ta-da! It's nice, isn't it? You're a bit skeptical, but...
How is upper function rho n depends on n?
Well, because the rho n here depended on n.
How it depends on n?
Not very much. How it depends? It's just because we were counting the number. Rho n counts the number of solutions. So let me remember the definition.
Oh, it's integer.
It's rare.
Sorry? What is the yeah, so this is how rho n was defined. Yeah, rho n is defined as the number of solutions to the equation, so it depends on big N.
Okay, but if n grows to infinity, then
it's
what is this function?
Nothing horrible. It's well, what we really care about is that it does not. It's never zero. If it, yeah, as I explained, let me see. Total. Okay, so as I explained, independently of big N, independently of what big N is, the tail of the infinite product will be bounded below by 1/2. Say, will be between 1/2 and 2. Because of the bounds we gave by using Weil backwards. So we just have to care about a finite number of terms. And in this finite number of terms, I claim they were all non-zero. And in fact, if they are non-zero, they can be bounded from below by, say, whatever it is, 1 over p or what have you. If there's at least one solution, modulo p, that means that the proportion of solutions is 1 over p. So it gives you some sort of easy floor. So, well, so my thing was, it's bounded from below by a constant that depends on little n and little k. You can do better than that, but just sitting here in the chair, that's what I'm telling you.
This function sigma n
it's bounded from below by a constant that depends only on little n and little k and is positive. It just follows from what I said before. I mean, from what we have seen so far. Yes, we still have to do the minor arcs, but yes, more questions?
No, it's a philosophy question.
Yes, that's good.
Okay, we have a form, cognitively form. Yes?
Sorry?
Say that for this form we have has a principle.
That's right, a quantitative has a principle, which is nice.
Okay.
Yes?
And is it true for all forms?
That's a very tricky question. Philosophically, that should be the case. In general, it starts being the case when you see, here we're assuming that little n is big, right? Because we were proving, all of the proof was valid. So we have, here we are assuming that little n is bigger than, is at least 2 to the little k. So we haven't, remember that. And now that we will do the minor arcs in the remaining non-existent time, well, no, 10 minutes, we will manage to do it. We will need to make a stronger assumption on little n. So the moral is, if you have lots and lots and lots of variables, the Hasse principle tends to the truth, philosophically speaking. Can one give a very general statement? It's a bit tricky, but yeah. Okay, so what about the minor arcs? In fact, we had the bound, and we will be quite brutal today. We will just use the L infinity bound we got from 2 lectures ago. So, well, this is just, first of all, in the minor arcs, here as usual, we cannot usually take advantage of the argument, so we have to take absolute values inside. And here we're going to be brutal. There are better ways to do it. You take the maximum over the minor arcs. The minor arcs, being part of the circle, have measure at most 1, of course. And by while, this is the part where I'm using while. This is 1 plus delta, where I'm really using while, before we use it as a trick. This is m to the n minus delta n over big K plus eta n. So assume, so now we make a stronger assumption that little n is bigger than little k, big K. So remember, big K is 2 to the k minus 1. We set epsilon really small, we get that n minus delta n over k plus eta n smaller than n minus k minus, say, 1 over 5k. The 5 has no importance, it could be 1. We're a bit clever, so we conclude, we are done. So I'm just saying, just by making n big enough, this little gain from while gets multiplied by little n, so it becomes bigger than minus k, which is what we need. So we conclude. This is a big conclusion. So the theorem, Harding Littlewood. The number of solutions in positive integers, so is equal to, well, there's this product which will be positive times, well, this closed expression, because we were lucky, but the important thing is that it's a volume, n, we can write scaling here, plus another term which is small, n k minus 1 minus a power delta prime so this is the main term and this is the error term. So a number of solutions is precisely what I was saying. So all I have done now is estimate the minor arcs. They give a small error and it's of the same kind as before. Very well. So that's it. Let me just give you, as usual, some of the later history of the problem. This is what Harald and Littlewood had almost 100 years ago. So let me be, actually, Huat's work came after Vinogradov's first work, so I'm going to be slightly ahistorical. But let me just first tell you, to give you a flavor of the thing, that there is one easy bound, one easy improvement that we can get. What do I mean by an improvement? Well, the result gets better and better if we prove this for small, so this is for n bigger than k to k minus 1. So to improving on these results means softening this condition. How far can we soften it? So how to get a softer condition? Well, I'm just going to tell you to have the integral of the minor arc, so I'm going to be a bit less brutal, not a lot. I'm going to take the max, but just with power n minus 2, and here I'm going to take the integral. Now, how does that help? It's because if you write this out, so again, doing things backwards always helps. So this is actually the number of solutions to an equation. The number of solutions to in integers. So what is the equation that whose solutions we are counting here? This integral is alpha squared. What is equation? What is it equal to? It's the number of solutions to which equation? x1 to the k equals x2 to the k. And of course, the number of solutions to that equation is exactly m plus 1. Right? The only way this is going to be true is if x1 equals x2. So that's great. So this integral is not m squared, this integral is m. So this gives you then 5L m to the 1 plus epsilon minus delta over pk into minus 1, and here we have m. This is m and minus 1. So using tricks of that sort, already Harald and Littlewood in fact prove something slightly better. Proved it for 2 to the k minus 1, k minus 2 plus 2. Very good. So later improvements were far more substantial. As I said, I will state the thing with Hua you can get. And this you will find in many expositions, including the two sources given here. So I forget the constant, but I think it's 2 to the k minus 1 plus 1. Yes. It's a far more sophisticated, well, the basic idea is that, it's just that he does something harder. Bounds, so not the integral of s alpha squared, but it's alpha 2 to the k minus 1. Yeah. Yes, so he manages to get something like well, m to the 2 to the k minus 1 and here he gets minus, so L is here. The basic idea, what is basic idea here? It's quite clever. It uses ideas from the proof of the first proof we gave of value inequality, but really combined with taking integrals and combined with this sort of simple idea. I will not go into the details. I'm just telling you about this. Sorry.
It's for big N only?
Well, this actually works always, but only for this n will it give you enough. You see, you get the gain. You get already a gain from this, from 2 to the k minus 1, but then you have to, the plus 1 is here, so you have room to apply the Weil bound. All right, let me explain.
It's if k is equal to, then you have...
Yeah, for L equals 1, you get exactly the same thing that we had. This inequality is true without the condition. I'm just saying that, so this is true for all L. It's just that this combined with the Weil bounds and put into the proof is enough when this is the case.
But if k equal 2,
Yes.
then you have n equal 3.
Yes, that's right. K equals 2, n equals 3. Good point. Maybe some constant is off here. Let me just be very cowardly. That solves problems, doesn't it? So I said I was not positive. I didn't write it down.
Really, the question is...
But probably you do get something. Actually, you probably, even in that case, you probably get a good minor arc bound. But yes.
The question is, can you prove the Lagrange theorem about four squares this method?
Actually, that's a very good question. You know, let me double check. I will look at it at home. I should know that, but let me double check that. Cubes you can do, but squares, can you do this? Actually, I should go and check. But small values of k are very tricky. Okay. All right. So Vinogradov did much better. So Vinogradov did. So I commented on this. So this is the first version of Vinogradov, but he worked on this throughout his life. And here, 1 plus of k log k. Yes. So, of course, it's a huge improvement. What happens is that he managed to give much better bounds than before for the sums, as in Weil, as I mentioned 2 classes ago, using some bounds that were not using some integration, some LP norms, and so on. All right, and the base bound here. So there's a series of works by other people. I'm just going to give you the base bound today. It's a factor of 2 better than Vinogradov. This is due to Woolley. This is the 90s, I think. Yes, I should just emphasize that here in these two cases, n is small enough that we don't actually get an asymptotic from this method, and I think we don't know the asymptotic, but we get an asymptotic so we do get existence, and we did get an asymptotic for a weighted number of solutions. Yes. For the unweighted number of solutions, we know asymptotics only start in about k squared. So already Hua, same Hua, but using not just his own ideas, but also Vinogradov, got here k squared log k, and I think the best result is k squared plus 2k minus 3. It's relatively recent, in the last 10 years. very well, and that's where things are right now. And other people that contributed here, I think Yingren Chen was also into this, and several others. I think Vaughan played a role. I just don't want to leave anybody out. But the really big jump came with Vinogradov. There's a huge difference between 2 to the k minus 1 and k log k squared. Yes.
Do you know anything about the law?
That's a good question. For the funny thing is that if you're asking for representations not just of large enough n, but for all n, then actually a bound like this one is tight. As in, already when n is smaller than 2 to the k minus 1, there are some small integers that don't get represented. But let us say that we just care about really large integers. I know that there are some bounds, but I don't know them off the top of my head. I will try to get them on paper. Yes. I mean, obviously, the trivial thing would be k equals n. That would be a lower bound. Yeah. So when can you get already things for little n equal to k plus 1? I have no idea. In fact, is there any hope of getting something linear on k in this case? That I don't know. There's a nice survey paper by Vaughan and Woolley, but it predates the strongest results by Woolley on the right. At any rate. So I think that will be it for exponential sums. I thought I would give another lecture on ternary Goldbach, but I already gave the colloquium talk here, and the slides are on the web. So I think it would be nicer if the next 2 classes, which are the last 2 classes because of the conference, were rather on growth in non-commutative groups. So it will be a bit of, it will be going back a little bit to additive combinatorics, but from a very different perspective.